Hello friends, my name is Sourabh Jain. I welcome you all in today's lecture of the lecture series started by the Laju College. In continuation to the previous lecture on stability, today we are going to discuss photostability, that is, the stability against the light, or more correctly, against the light reactions. So, let us start our discussion with the basic regulatory requirements to market a pharmaceutical product, which can be either a bulk drug or the drug product. We discussed earlier also that the safety, efficacy, and quality, these are the three basic requirements to market any pharmaceutical product, and these requirements should be complied with not only at the time of their manufacture but until their consumption by the patient. That means the pharmaceutical product should be stable also. As we know that pharmaceutical products may show changes in their physical, chemical, and microbiological characteristics with time. But here in this lecture, we will discuss the changes occurring only due to the light. We will focus on mainly the chemical changes, that is, on photochemical degradation. Later, we will also discuss the techniques or the approaches to prevent this photo degradation. We all know that the chemical changes or the chemical reactions are the transformation of one set of chemical substances into the another, and this transformation involves formation and breaking of the bonds in the form of the electrons. We should keep in mind that the chemical changes has nothing to do with the nuclei of the atoms. That means the elemental change is not going to occur in chemical reactions. Chemical reactions occur only and only when a minimum amount of energy, that is, activation energy, is available to the system. Now, depending on the source of this activation energy, the chemical reactions can be of two types, that is, the thermochemical reactions and the photochemical reactions. In the thermochemical reactions, the activation energy is provided by the collision of the molecules, which in turn is provided by the heat or the temperature of the system. While in case of photochemical reactions, the activation energy is provided by the electromagnetic radiations of appropriate wavelength. Thermochemical reactions can occur in the absence of light also, and their rate of reaction is not affected by the light. So, these reactions are also called as the dark reactions. The temperature of the system has a significant effect on the rate of reactions. On the other hand, the photochemical reactions can take place only in the presence of the appropriate electromagnetic radiations. They are also called as the light reactions. The temperature of the system do not have a significant effect on the rate of the light reactions. Now, as we discussed that the light reactions take place only in the presence of the appropriate electromagnetic radiations, the energy of these radiations should not be too less or too high for the excitation of the outer cell electrons. So, the spectral region involved in the photochemical reactions ranges from 200 to 800 nanometer of the wavelength. The spectral region comprises of spectral region comprises of the UV region ranging from 200 to 400 nanometer and the visible region ranging from 400 nanometer to approximately 800 nanometers. The UV region is further subdivided into three different bands, that is the UVC, UVB and UVA, which ranges from 200 to 200 to 290, 290 to 320 and 320 to 400 nanometer respectively. Out of these, UVC is most energetic and most harmful also, but fortunately most of the UVC do not reaches the earth's surface because of the absorbance by the ozone layer. Along with the wavelength, the intensity of the radiations also affect the rate of the photochemical reactions. When light falls on any substance, only the fraction of the incident light which is absorbed by the substance can bring about a chemical change. Reflected and transmitted light do not produce any such effect. Further, all light radiations absorbed by the reacting system may not bring about a chemical change. When the conditions are not favorable, some portion or the whole light absorbed is converted into heat or is re-emitted as radiations. Now let us discuss the importance of photochemical reactions in the development of pharmaceutical dosage form. There are a large number of drugs which are sensitive to the light, and such drugs may degrade during manufacture, distribution, or even at the time of administration of the drug to the patient. The photodegradation of the drug may reduce the potency of the drug product. At the same time, the product of the photochemical reactions may be toxic itself, or it may cause phototoxic, photoallergic, or photosensitization reactions upon administration. The European Pharmacopoeia prescribes the conditions of light protection for more than 250 drugs and adjuvants. The knowledge of the photochemical behavior of the drug may be useful in their stabilization, and it can also provide the guidance for handling, packaging, and labeling of such drug products. So, the evaluation of photochemical stability of the drug and drug product is an essential component of the formulation development process. The chemical structure of the drug and the nature of the dosage form are the major determinant of photosensitivity of a drug or a drug product. The presence of some chemical functional group in the drug molecules are usually necessary for occurrence of photochemical reactions. Some of these groups are double bond, carbonyl bond, aryl chloride, and nitroaromatic groups. The photosensitive drugs may undergo photochemical reactions by various pathways upon exposure to light. These reactions may proceed as photodegradation reactions occurring through the formation of free radicals, or as photosensitization reactions occurring through intermolecular energy transfer. Formation of the final reaction product can occur through several steps involving primary photochemical reactions followed by the secondary thermochemical reactions. The major modes of the photodegradation of drugs are, for example, photoaddition, photocyclization, photodecarboxylation, photodehydrogenation, photoelimination, photoisomerization, photooxidation, and photoreduction. Now we come to the second part of the presentation, that is the photostabilization or prevention of photodegradation. The photosensitivity of a drug makes it necessary to take appropriate measures for their stabilization. The common approach to afford photostabilization is the use of suitable primary and secondary package. Pharmaceutical products can be categorized into three classes depending on their photosensitivity. Class 1 includes the products which are stable outside their primary package. Class 2 includes the products in which primary package protect the content from photo degradation, while the class 3 include the products in which primary package is not sufficient and secondary package provide the required protection. Protection of product from light can be achieved by the use of opaque or amber colored containers. Amber glass is suitable for drugs absorbing in the UV region as it prevents the transmission of light below about 470 nanometer. An opaque secondary package may also be used for this purpose. Light transmission tests may be applied to evaluate the light transmission characteristics of the containers to be used for photosensitive drugs. Next is the use of opacifying and coating agents in the photostabilization of the drugs. The yellow, red and black iron oxides have been employed as opacifier for the protection of Sourabh, molcidomine and nifedipine tablets. These are most effective on even distribution over the surface of the drug particle in the tablet matrix. Another method of photostabilization of tablet formulations involve film coating with opacifying agent. Photoprotection of solid dosage form may also be achieved by the use of opaque capsules. Next approach is the application of the principle of spectral overlay. It is based on the use of excipients that exhibit the absorption spectra similar to that of the drug. This results in the absorption of the light by the excipient at the expense of the drug and thus protecting it from photodegradation. For example, molcidomine tablets can be stabilized by adding UV absorber Usolex 9020, which is actually 4-tetrbutyl 4-methoxydibenzoyl methane. Likewise, the photostabilization of diclofenac gel has also been achieved by the use of a UV absorber Usolex 6300. Food colorants have also been employed as photostabilizing agent for the oral dosage forms. The addition of such excipient is also useful in the formulation of the creams, ointments and liquid dosage form for protection of the photosensitive drugs. Next is the technique of complex formation. Caffeine has been employed as a complexing agent for the photostabilization of riboflavin, which is a highly photosensitive drug. Here, the complexation occurs by the formation of the stacking complexes. The photostabilization of the drug can also be achieved by the formation of cyclodextrin inclusion complexes. Cyclodextrins are the cyclic oligosaccharide molecules which have relatively hydrophobic interior and hydrophilic exterior. This structure imparts to them the capability of forming inclusion complexes with the hydrophobic drug molecules and thus protecting them from photodegradation. Numerous examples of photostabilization of drugs by cyclodextrin complexation have been reported. These include the complexation of clofibrate, nifedipine, pyridoxine hydrochloride, doxorubicin, mitomycin C, and many other photosensitive drugs with different cyclodextrins. The next approach is liposome formation. Liposomes are the microscopic and submicroscopic phospholipid vesicles with a bilayer membrane structure. Photostabilization of the drug substance by entrapment into liposome is an effective method to improve their photostability. Example of stabilization of some photosensitive drug in liposomal formulation includes riboflavin, vitamin A palmitate, amlodipine, and many other drugs. Next approach is the use of stabilizer. A careful consideration and control of the factors that promote the photodegradation of drug may improve photostability. For example, some factors that promote photooxidation of drugs includes oxygen, oxidizing agents, and metal ions. So, removal of oxygen present in the formulation by purging with nitrogen, or the addition of suitable antioxidants, or the addition of chelating agents can reduce the photooxidation. Next approach is the choice of appropriate solvents. The photodegradation rate may be affected by the polarity and or the viscosity of the medium. The use of a solvent or a solvent mixture having appropriate dielectric constant and or the viscosity may improve the photostability of a particular drug. For example, the photodegradation of cyanocobalamin, that is vitamin B12, in aqueous solution is suppressed by the addition of glycerol due to an increase in the viscosity of the medium. Last but not least is the choice of the pH. pH of solution is an important factor in stabilization of the drug substances. A drug may be more stable in its ionized or unionized form. For example, ascorbic acid undergoes rapid photooxidation in the neutral and alkaline pH, but it is stable in the acidic pH. So friends, this is all about the photostability. I hope you have enjoyed the video. In case you are having any doubt, any query, please feel free to contact me at my mobile number 94145067030. Stay home, stay safe. Thank you. Thanks a lot.